We just learned how to work with probabilities, and now we'll talk about probability distributions. We're going to start with the discrete random variables. So these are the distributions where the outcomes are whole numbers. Specifically, we'll learn how to work with the binomial and the Poisson distributions. Binomial distribution got its name because it models two outcome situations. These are also called Bernoulli trials, and it got its name the binomial because we have two nominal outcomes. So our outcomes are normally success failure, male female, infected uninfected, survive or die, etc. What this distribution does is try to model the number of successes we have in n trials. So in mathematical notation, we're looking for the probability p of k successes in n tries. In order to calculate this probability, we have to know the probability of a success, or the probability of one success in one try. That will be p, lowercase p. So here's an example using fish parasites. We could assume that about 10% of the infected fish are infected with the parasite. If we go out and sample 3 fish, then what's the probability of getting 0 infected fish, 1 infected fish, 2 infected fish, 3 infected fish in our sample? So one way we can approach this is by brute force, which is basically draw out the possibilities and then perform our probability calculations. So we know that out of 3 fish we have a different number of outcomes. If we look at 0 infected fish, then all of our fish have to be uninfected. If we have 3 infected fish, then all of our fish have to be infected. If we have 1 or 2 infected fish, then when we look at our fish, we can have, for example, this 1 infected, we could have the first fish that's uninfected, second fish that's uninfected, third fish that's infected. Or we can have the first fish that's uninfected and the last fish that's uninfected, and that means the second fish is infected. Or the very first fish could be infected and the last 2 can be uninfected. So what you can see is that there is only one way to get 0 infected fish, and there's only one way of getting 3 infected fish. But we had 3 different ways that we could generate 1 infected fish, and we had 3 ways in which we can generate 2 infected fish. We have to account for this when we calculate our probabilities. So how would we do the probabilities? Well, if we did it by hand, we would use our multiplication rule. So for example, with 0 infected fish, we would do the probability that the first fish is uninfected times the probability that the second fish is uninfected times the probability that the third fish is uninfected. Well, what's the probability of uninfected? Well, we go back to our problem. We said that the probability of infected is 0.1, or 10%. And that means, since we only have 2 outcomes, that 1 minus this value is the probability of being uninfected. So to get that probability of 0 infected, we have 0.9 times 0.9 times 0.9, or 0.729. If we were interested in the probability of 3 infected fish, well, again, it would be 0.1 times 0.1 times 0.1, because all 3 fish have to be infected. It uses the and, so we follow the multiplication rule. For the 1 infected fish, what we know is that we have 1 fish that has to be infected, so that's 0.1, and we have 2 fish that have to be uninfected, so it's 0.9 times 0.9. But that's not all. That's just for one sequence. We have to multiply it by 3 because we have 3 combinations, and we get 0.243. If we have 2 uninfected fish, same type of situation. 2 of the fish have to be infected, so it's 0.1 times 0.1, and then that last fish has to be uninfected, but again, we're not done. This only gives us the probability for one outcome, but we have 3 different possibilities. There are 3 different ways to get 2 infected fish, so we multiply this probability by 3 to get 2.43. Now, the brute force is pretty easy when we have a small number of samples, or we have a small number of out of situations like this. where we had out of 3 fish. But as we increase our out of number, we can't really do the brute force anymore. It starts to become too difficult to try to figure out all the different numbers, all the different combinations for our possible outcomes. And this is where our binomial distribution comes into play. So here's our equation. Don't worry about this right now. This is our combinations, but I want you to focus on this part. So P is the probability of success, or the probability of being infected. K is how many individuals have to be infected. 1 minus P is that not infected part of it, and N minus K is those individuals that are not infected. So going back to our actual brute force, you can see that we have 0.1 for the 0 of 3 infected, 0.1 raised to the 0. Well, that part says that we have 0 fish that are infected, so probability of being infected is 0.1 raised to the 0 power because none of them are infected. 0.9 is the uninfected probability, and we have 3 of those, so we raise it to the 3rd power. This 1 is the combinations. Since we only have one possible way to get 3 uninfected fish, we multiply it by 1. For 1 and 2, you can see the same thing. 1 infected fish, well, it's 0.1, that's our probability of being infected, raised to the 1st power. And we have 2 uninfected fish, so 0.9 squared. And then we have 3 combinations. So you can see how I drew it, how I wrote it out here in longhand form. It starts to match our actual equation. So this is our equation that we will use. This N over K part is choose notation. This is going to give us the number of combinations of getting K successes in N trials. You will see this written other ways, where it could be N choose R, like it is on our calculator, but I use N choose K because that matches some of the functions that we'll use in R. We then have P raised to the K, so that's the probability of getting the number of successes that we needed, and then 1 minus P raised to the N minus K accounts for the number of failures. So if we have 5 as our out of number, if we were doing 3 infected fish out of 5, we'd have our probability of being infected raised to 3, because 3 fish had to be infected, and that meant 5 minus 3 equals 2. The other 2 fish had to be uninfected, and then we would do the choose notation. Now, how do we use this choose notation? You'll notice that this notation does not have a line because it's not a fraction. This is a separate type of written format for combinations or combinatorics. The long way to do it would be to use factorials. So N choose K would be N factorial divided by the product K factorial times N minus K factorial. What this basically does is figures out all of your combinations. Now we can do factorials on our calculator. We have the exclamation point button on my calculator. You may have just the exclamation point on the calculator. And you could do that. You can do that longhand. The factorials basically take your n times n minus 1 times n minus 2 all the way down to 1. So it makes it easy to use the exclamation point button on the calculator. If we wanted to do it in R, well, there's a factorial function in R that will do it for us. We can do it longhand by taking the product of n to 1, so basically the product of all the numbers counting backwards, which is exactly what the factorial function does. Or we can use the choose notation. We're going to use the choose notation to calculate these combinations. So on our calculator, what we're going to do is look for probability settings and then the NCR button. So the N, big C, lowercase r. Here's the N choose R, or number of trials, choose the number of successes button, or the option, depending on the calculator. How we would use it is to give the out of number, N, push that NCR button, and then give the number of successes. Alright, so I say try it to confirm that there are 3 ways to get 1 out of 3 infected fish. How would we do that? Well, the out of number is 3. We've got 3 fish. NCR, and then 1 infected fish is what our target is. And when you do that, hit the equal key, you should get 3. So this might be a little bit easier with some practice problems. So here's an example. Say you sampled 10 fish. What's our probability that 3 of those fish are infected? And again, we'll use the same probability being infected, which is equal to 0.1. So you can think about it, how to do it by drawing out the equation. Here is the actual equation that we would use. So we're looking for the probability of 3 of 10. So it's 10 choose 3 times the probability that we get 3 infected fish times the probability that we would get 7 uninfected fish. So note 3 plus 7, that equals 10. 0.1 plus 0.9, that equals 1. We follow all of our rules. So here's the equation that we would use. In the calculator, we can just do everything using multiplication. So on my calculator, I would use 10 NCR 3 times 0.1 x raised to the y 3 times 0.9 x raised to the y 7 and hit the equal sign, and I get 0.0574. Confirm that you can get this number. So how could we do this in R? R has a very useful function called dBinom. dBinom calculates the actual probability, or the density, using the binomial distribution of x successes out of n trials, where the probability of success is equal to some value. You'll note that this looks familiar. So if I look at the help file, you will see that we have a number of different binom functions here. dBinom, pbinom, qbinom, and rbinom. So up to this point, we've seen the R function. So we've seen rnorm, rexp, and a couple other ones. We're now working with D, which gives us the probability or the density. That's what D stands for. It does X, which is our event, the number of successes. Size represents the out of number. And prob is the probability of success. Now you have some examples down here that you can look at, but we're going to use dBinom for our problem. So we just calculated this by hand. Now let's do it in R. So it is dBinom, 3 successes out of 10 fish, and our probability of being infected is 0.1. And we get the exact same number that we would have gotten when we did it in our calculator. So now, as practice, using your calculator and using R, calculate this probability. So we will assume the probability of being infected is 0.1. And now we say, well, what's the probability of getting 5 infected fish out of a total of 10 fish? Pause the video. First do this on your calculator, and then try to use R. Alright, so I won't do it in the calculator, but it will do it in R, so we can check our work. Again, it's dBinom. We want 5 infected fish out of a total of 10. Our probability of being infected is still 0.1. So you should see that our chance of actually getting 5 out of 10 fish, if the probability of infection is 10%, is equal to 0.001. We have one more example that you can calculate. This changes things a little bit. So now we can look at clutch sizes. So when we look at clutches, normally our clutch size is fixed. That's our out of number. And then we can ask things like, what's the probability that we have a certain number of males or a certain number of females in that clutch? So for this example, I asked, what's the probability of getting 5 females in a clutch of 8 offspring? Well, the one thing we have to know is the probability of actually having a female. So if we have one offspring, chance that it's a female, typically 0.5. All right, so then we're looking at what's the probability that we have 5 out of 8 females? Well, D binom 5, 8. So 5 females out of 8 offspring, probability of success is 0.5. I'll let you do this in R. If you have problems, please email me. Alright, so what do we know about this binomial distribution? Well, this distribution is defined by 2 values. It's defined by the out of number, and it's defined by the probability of success. And that's the probability of success of one success out of one trial. Using those 2 numbers, so the out of number and the probability of success, we can multiply them to get the mean. And that's for the population. We can multiply n times p times q, where q is 1 minus p, to get the standard deviation. So these 2 properties will show you that as we our widest part, the highest variance that we see is when our probability of success, when p, is around 0.5, right in the middle. As we start moving to the ends, we start compressing our distribution. Variance goes down. What does this mean for us? Not a whole lot. Mathematically, what this says is that if our probability of success is between 0.4 and 0.6, we could utilize a normal distribution as an approximation for the binomial. That used to be required in the past when we didn't really have computers, but now there's no point in making that approximation. We can do binomial distribution in a calculator. We can do it in R. So it doesn't really matter a whole lot. But for us, what it also means is that anytime we use a binomial distribution, we have to give it 2 different values. We have to give it the out of number, and we have to give it the probability of success. So that's a key point. Also, if we have data but we're not given the probability of success, then what we can do is take our frequency table and calculate the average. Then when we take the average and divide by the out of number, that gives us a probability of success that we could then use for all of our calculations. How would we use this? Here's a typical example of how we would use it. We would go out and collect some data, collect data on 2 outcome situations, so infected, uninfected, or in this case, looking at fruit set. We have our observations, so our observations would be a column, and then what we would do is test one of 2 things. We can test whether or not our data are random, or we can test if our data follow some prior expectation. So for example, we went out and we recorded the number of fruit that's produced by individual flowers on prickly pear cacti. We know that these cacti have 10 flowers. We'll assume that they always have 10 flowers, but not all of those flowers set fruit. If our probability of fruit set is equal to 0.5, then does our data match this probability of fruit set of 0.5? So we have our observation, so this is our frequency table. We're given the probability of fruit set. Question is, what's our out of number? Well, the out of is this first column. So 10 is the maximum. It has 10 flowers. We can have 0 fruit, 0 of those flowers setting fruit. We can have all 10 setting fruit. So what we would do is recognize that these data follow binomial distribution. We have two outcomes, fruit or no fruit, and we have an out of number. It's out of 10 flowers. We would then use the binomial distribution to calculate these probabilities. How would we do it? Well, it's actually not very difficult. So I give it in the PowerPoint presentation, but we can also write it here. So cactus example. We want to know the probabilities. Alright, so we have our probabilities. We're going to use dbinom. That's our function for the probability. And we need to know the probability of all of our possibilities. So our possibilities are 0 to 10. And this is kind of a shorthand that says give me the probability of the sequence. So we're going to calculate the probability of 0, then the probability of 1, then the probability of 2, all the way up to 10. Our out of number is 10, and our probability of setting fruit is 0.5. When I run that, I get all of these probabilities. Those probabilities get entered into our table, but we're not done yet. What we have to do is figure out our expected number of flowers that set fruit given these probabilities. So our expected column is our total number of observations, so big N, times the probability of each event. So P sub x is the probability of 0 fruit, the probability of 1 fruit, the probability of 2 fruit, and so forth. What's this N? Well, that's this column. This is the sum of the observation column, gives us our total number of observations. So this is how many plants we observed. We know from previous presentations that probabilities actually represent frequencies. So what we're looking at is if these are the probabilities, then we want to know what frequency of our total should correspond to 0 fruit, to 1 fruit, to 2 fruit. That's what these numbers are. How could we do it and by hand? Well, what we have to do is first figure out what our total sample size is. So we will go first calculate the sum of that column. So I'll make the column and then do the sum. So we're going to calculate expected numbers. I'm going to do big N. This will be the vector 50, 70, 116, 192, all of these numbers. All right. And what we want is the sum of that vector. And I'll check it. 2,000 values. So now we want to know the expected. And that expected is our probabilities times our total sample size. And we get all of these numbers. We could do it by hand, but we're in R, so might as well go ahead and do that. So here's all the numbers. From this point, then we would go to that next step and say we have our observed, we have our expected, assuming a probability fruit set of 0.5. Then what we could do is do a goodness of fit test. We can do a chi-square test or a g-test to see does our observed data match what we expected given our assumptions. We're not going to do this now. We'll do this later. So we'll come back to doing these probabilities. I'll note two differences. Well, one difference. So first, the similarities. Our probability of actual fruit set is 5. So if we calculated the average of our observed data, we would get average of 5 fruit per cactus. So an average of 5 out of 10 flowers will set fruit. This is the same average that we would get from our expected values. Can we calculate it? Yeah, you can calculate it using these numbers. Or we know the probability of fruit set is 0.5. Just multiply it by the out of number, which is 10. So that's the little n times our p, that gives us our average. So we get the same average, but notice the difference in our standard deviations. So standard deviation in our actual statistic is 2.1. So standard deviation of these data is 2.1. Standard deviation of our expected value is 1.58. Again, this is n times p times q. So what you can see is that we have more expected in the center part of our distribution and fewer in our tail, so it seems like we're clumped. Now, is this a big deal? Well, it just kind of comes down to the biological explanations. So this is something we're interested in, we would go ahead and pursue it. So I make a note of this because our goodness of fit test is going to test the mean, and it's also going to test the distribution. Alright, so our application is to generate expected values so that we can do hypothesis testing. The hypothesis testing that we can do comes up with two different types. So one is our data random? This type of question assumes that our data actually follow the probability distribution that it should follow. So in our previous example, it should follow a binomial distribution. If we ask the question, is our data random, then chances are we will have to calculate our probability of success from the data. So we would calculate the mean, we get 5 fruit per cactus, and then figure out and use p equals 0.5 to generate our expected values. So that's one part of testing a hypothesis. The second hypothesis test that we can run is testing if our data follows some expectation if the probability of success is some value. So we can test, is the probability of fruit set actually equal to 0.5, or is it some other number? It's two different ways of doing a hypothesis test, and our answers, whatever the result of that test is, leads to different conclusions. So hypothesis testing we won't do just yet. We will, but these are possibilities. This is where we're going. The other way, and the way in which we'll use this binomial distribution for this next exam, is to calculate straight up probability. So this is just basically to give you practice calculating and using the binomial distribution. For example, I could ask you, what's the probability that we get at least one fruit on our cactus? I could ask you, what's the probability of getting 3 or more boys if we have 5 children? Or I can ask you, what's the probability that we have an uninfected individual, all uninfected individuals in a sample size of 10? These are all just basic probabilities that we will use the binomial distribution to calculate. Alright, so now here's some practice. We're going to assume that we have clutch size of 7, that the organism always has a clutch size of 7, and we went out and we sampled these clutches and recorded how many male offsprings they had in that clutch. And here's our frequency table. So we had 4 clutches with 0 males, 19 with 1, 39 with 2, 44 with 3, 29 with 4, 12 with 5, 3 clutches with 6, and 0 clutches with 7. So what I want you to do is to calculate probability of 0 males, 1 males, 2 males, and so forth, and then the expected number of clutches given that probability. We're going to do it two ways. One way, we're going to do it given the data, so you're going to have to calculate the probability of success. The second way is to assume that the average number of males is equal to 5. We're going to use that assumption to calculate our probabilities and to generate our expected numbers. So I think what's easier is to go ahead and work with this one first, do the probabilities, and calculate expected numbers. I want you to be able to do this by hand and in the calculator. So pause the video, work on this. Alright, so you've taken some time, try to calculate these probabilities. Let's see what I get. So these are my numbers. I used R to do these, but we would get the same numbers if we used our calculator. So how did we do it? So here's the general flow for these types of problems. One of the things I like to do is convert my table to a vector. It's not always required, especially if we were only if we were given the probability of success. We don't really need to do this. We just need this column to get our total that's used for the expected numbers. But I know we're going to have to calculate the mean from the data, so I went ahead and converted my table to a vector. Alright, so first up was we're assuming that the mean number of offspring, mean number of males per clutch is 5. So what this is asking is the probability of being male equal to 5 over 7? How did I get 5 over 7? Well, 5 is the mean. Our out of number is 7. So 5 divided by the out of number gives us the probability of success in one try. So the first thing we do is calculate our probabilities. I use the dBinom function, and you'll note that I use 5 over 7 as the probability, and I get those data. There they are. And then I calculate the expected numbers. So this is my expected, and you note that I did the sum of the frequency, and if I run that, I get numbers that are decimals. When we do goodness of fit tests, we typically want whole numbers since our data are whole numbers. So I rounded here to get our numbers that I listed in the table. So running the whole chunk, here's our probabilities. There is our expected numbers. Now if we use the data, then what we're asking is our data random? Does it follow a binomial distribution? We don't have our probability of success, so we have to calculate it. How do we do that? Well, as I told you, it's the mean of our data set. And in order to do this, and in order to calculate the mean, I had to first convert our frequency table into a vector, which is what I did. So take the mean of our vector divided by 7, that's our out of, and this is the probability of being male given the data. Then I did the exact same thing as above, calculated my probabilities using the dBinom function. Then using those probabilities, I then calculated the expected numbers, again using the sum of the frequency, and you'll note that I used mean of our vector over 7 for the probabilities, and again I rounded. So our probability of being male given the data was 0.403. These are our probabilities, and these are the expected numbers. Now, as we'll note, is one of the things that we can do is just compare our observed to our expected. So if our probability of being male is actually equal to 0.5, or I'm sorry, 5 out of 7, then look at how many more we expect at the upper end compared to what we actually saw. So if we assume the probability of success is 5/7, this is what we'd get. It looks like, since we have a lot more up here than what we actually have in our observed data, it looks like the probability of being male is actually less. And we can kind of derive that conclusion just by comparing observed to expected. Now compare these two. Look, our observed values seem to be right on track with our expected values. I had no big surprise. I generated these data using the actual binomial distribution, but it's to show you that using the data, we should get similarities, at least for the mean. Our variance could differ. Alright, so that's our binomial distribution. Let's move on to the Poisson distribution. Poisson distribution will approximate the binomial distribution when our probability of success is less than 0.1 and our n times p value is less than 5. Now this is fine if we were going to approximate stuff, since Poisson's a little bit easier to calculate. We don't need the choose notation, but again, with calculators and our computers, we don't really need to make this approximation. We can calculate it. By hand or in R. So what did these two things mean? Well, it basically means that we're modeling a rare event. it's an event that where the probability of success is pretty small given the total possibility of outcomes. It also models events that don't have a fixed sample size, or I should say, they don't have an out of number. So for example, if we were to try to ask what's the probability that the phone will ring in 1 minute? This is a Poisson distribution because the phone might never ring. So the total number of possibilities is infinite. And that means the probability of phone ringing itself is going to be a very rare event because it's basically infinite. So a key distinction when deciding to use a Poisson is basically we don't have an out of number, whereas a binomial needs that out of number. When do we use the Poisson distribution in biology? There's really two different cases. One is for testing spatial distributions, and second is to test temporal distributions. So really what we're looking at is randomness in a spatial landscape or randomness through time. So for spatial aspect, anyone that's had ecology has done this. It's part of our ragweed lab. If individuals are randomly distributed across a landscape, then it should follow Poisson distribution. The temporal events are all of these time to events. So how long does it take before the event occurs? It could be time between lightning strikes or time to the next lightning strikes. For us, in biology, it's often time to death. So you infect individuals and then you record their day of death if they happen to die. This is Poisson because the individual might never die. So we have an infinite number of time, which means the probability of actually dying could be considered a rare event. So if our Poisson is measuring rare events, then our average has to be less than the maximum value that we can have, which by definition is rare. So if we consider trees in a grid, we put a grid down and we record how many trees are in the grid. Our grid has to be large enough to realistically contain a high number of trees. So we're not going to use a 1 meter by 1 meter grid to try to look at spatial distribution of live oak trees. I mean, a 1 meter by 1 meter might not even contain an entire an old tree. But we don't want the grid so large that we have basically zero variation. So when we choose our grid size, we want to, it's kind of just take some practice to figure out the right size. Also, when we model these distributions, the probability of occurrence must be independent of all other prior occurrences. So if this is our random distribution, the probability that we find this point has to be independent of all other points in its area. So we can't have any sort of social pattern or distribution dispersal types of patterns where individuals tend to clump together, or in the situations where the presence of one tends to make it less likely to find another. When we deviate from randomness, we can have either clumped or aggregated distribution. This is, you find one, you're more likely to find another. Or it could be a uniform distribution, where you find one and it's less likely to find another close by. All of these situations, we'll talk about how we can determine this by calculating what's called the variance to mean ratio or the coefficient of dispersion, and we'll then use this after we use goodness of fit tests later on in the semester. So how do we calculate the Poisson probabilities? Poisson probabilities model the probability that we have x events, and it uses lambda, which is the mean, raised to the x, divided by x factorial e to the lambda. So lambda, that's our mean number of events per sampling period, so the mean number of trees per grid, the mean number of seconds between lightning strikes, and so forth. X is the number of events that we're trying to calculate. All right, and I'll show you how to do this by hand. In R, we use the dPoise function. So dPoise is Poisson distribution, poise. D is our density or probability, and we give it the x value because that's what we're trying to calculate. We also give it lambda, which is our mean of the data. So you'll note that we don't have an out of number anymore because the Poisson doesn't have that out of number. There is no defined out of number here. Lambda is our expected number. Now, if we don't have lambda, what we can do is just calculate the average of all of our data, or the average of our frequency table. So how could we do that? Well, let's consider an example. Let's say we infected 20 chickens with a highly pathogenic H5N1 virus, and then we recorded how many chickens died on day 0, day 1, day 2, day 3, day 4, and so forth. This is our data. So we can see that 3 chickens died on day 0, so within the first 24 hours. 9 died on day 1, 7 on day 2, 1 on day 3, and 0 on day 4. So we had a total of 20 chickens. We could ask 2 questions. First question would be, are these data random? So in order to calculate this, we would have to first calculate our average day of death, and then calculate probabilities and expected values. So can we do this in R? Of course. So we are now on the Poisson distribution. And we are going to do the example. So first up, we are going to convert our frequency table to a vector. So I got my X frequencies. Not sure what my frequencies are. Not sure what happened there. I'm going to move this off the screen as I enter in my numbers. Get this back here. All right. So my data, X and frequency, run this. All right, so I've got my vector. All right, so I made my vectors. Now I need to calculate probability. So calculating probabilities, we are using the dpoise. We want 0 to 4, and we have to give it lambda. And lambda is the mean of our data vector. And when I run that, I get these numbers. These are the probabilities. The next step with these probabilities is to calculate the expected numbers. So, not calculating probabilities, calculating expected numbers. So calculating the expected numbers, we're going to use the same dpoise function for probabilities times our sample size, which is 20 chickens. So this will give us how many chickens we expected to die at each time point. So we expect 5 chickens to die at day 0, 7 to die at day 1, almost 5 to die at day 2, 2 to die at day 3, and about a half a chicken to die at day 4, or we can say 1 chicken died at day 4. So in R, you can see that calculating these probabilities is actually fairly simple. Can we calculate it by hand? Yes. And I'm going to show you a trick on how to calculate it. So in our data set, the mean day of death is 1.3. That is lambda. We'll use the Poisson equation to calculate our various probabilities. So the first probability that we calculate is the probability that we die on day 0. We would substitute our values into our equation to get this equation. Now with the zeros, anytime we raise a number to 0, that's always equal to 1. Anytime we take factorial of 0, that's by definition 1. So this first p of 0 falls out to be 1 over e raised to the 1.3, which is equal to 0.273. We then move to the probability of 1. Now we can use the equation but what we can see is that we've just multiplied our previous value by 1.3 over 1, or lambda over the new x value. And I get 0.354. Continuing, I can write out my equation. But what you will notice, if I expand this, it is the previous answer, let's fix that, times lambda over the new x value. So hopefully you're seeing a pattern here. Let's continue. P of 3 is 1.3 cubed over 3 factorial times e raised to the 1.3, which is the previous answer times lambda over our new value. So again, there is a pattern emerging that allows us to easily fill out these frequency tables if we're calculating probabilities using the Poisson distribution. And lastly, P of 4, which is the same thing. 4 factorial times e to the 1.3, which is the previous answer times lambda over 4 1.3 over 1 and 1 over e to the lambda, and 0.032. And then for the expected numbers, I multiply these probabilities by 20 to get our expected number of chickens that would die on day 0, day 1, day 2, day 3, day 4. Alright, so just quickly review. When you do this by hand, first thing you do is start at the 0, calculate this probability, that is that. So then we multiply the previous by our lambda over the new x, so 1.3 over 1. This new one are those two. 0.23 is that. 0.1 is that. So if you do this on the calculator, you get 0.273 first, you leave it on the calculator, you multiply by the lambda over 1, hit equals, you get our new value. Then you leave that on the calculator and you multiply by lambda over 2, hit equals, you get your next value, and so forth. So the pattern for the Poisson is pretty easy. Am I going to make you fill out one of these tables on the exam? Probably not. It takes a little bit of time. But if I was, the Poisson's probably going to be the one that you calculate, because there is this pattern that really simplifies calculations. So after finishing the video, I noticed that I had a mistake here, and it is right there. We should have one more value to correspond to the 0.1. So we should have a 1.3 divided by 3 in place, in between that location. Pattern still stays the same, but just for completeness, this is the corrected video. Alright, so we saw how to calculate these Poisson frequencies by hand. what we need to do now is talk a little bit about the Poisson distribution. Binomial distribution, we said, is defined by two values. It's defined by our out of number and the probability of success. Well, with the Poisson, we don't have that out of number, which means we are only defined, or that this distribution is only defined by lambda, or the mean. With our Poisson distribution, this lambda has important properties. Specifically, the mean, lambda is equal to the mean, and lambda is equal to the variance. So the mean and the variance are the same if we're working with the Poisson distribution. You can see this in a sequence of curves as I increased our lambda value. We start out with a very peaked curve, and as our lambda increases, we get a wider and wider type of distribution. This means that we can use the property of the Poisson distribution to determine if our data appear random, if they appear clumped, or if they appear uniform. We can do this by calculating a variance to mean ratio. This variance to mean ratio is also called the coefficient of dispersion. So if the coefficient of dispersion follows a Poisson distribution, then we said the variance is equal to lambda and the mean is equal to lambda, which means our coefficient of dispersion will be close to 1. If our variances exceed our mean, then we're clumped or aggregated. Well, why is that? Well, if we were to calculate the distance between each point and its neighbors, you will see we have a bunch of really small distances because we have groupings, and then we have a bunch of points, bunch of distances that are very large. So you've got the variance ends up exceeding the average distance, leading to a coefficient of dispersion greater than 1. The opposite is if all of our distances are about the same. So here the distances between each of our neighbors are a mix of smaller distances and a mix of larger different distances, but most importantly, all of the distances tend to be about the same. That makes a variance of the distances very small because there's very little variation with that. And our variance becomes less than the mean. So our relationships, coefficient of dispersion equals 1, we appear random. Coefficient of dispersion greater than 1, we're clumped or aggregated. Coefficient dispersion less than 1, we're uniform or repulsed. Alright, so now for some practice. Let's go ahead and calculate probabilities by hand and calculate probabilities in R and calculate the expected values for each. Now, just like the binomial distribution, it comes down to two different types of hypothesis testing. For the first hypothesis test, we can ask if these data are randomly distributed, in which case we will calculate lambda from the data and then generate our probabilities and our expected values prior to performing the goodness fit test. The second hypothesis that we could ask is the lambda equal to 3? Or in another case, is the average number of trees per grid equal to 3? Now we'd use our hypothesized lambda to calculate the probabilities, calculate the expected values, and then use the expected and the observed to do a goodness of fit test. So pause this video, try to do these probabilities by hand and also in R. So you've had some time to calculate these probabilities and expected values. These are mine. When I calculated it by hand, I came up with the same values as how I did it in R. So here's how I did it in R. I started by converting the table to a vector. I had to do that because I needed to calculate the mean in order to complete the first two columns. So the first step was to calculate the probabilities using lambda equals the mean of my data vector. This would ask the question, or test the hypothesis, are the data random? So I generate my dPoise values, my probabilities, using this function. And then I calculated the expected value by using the same function and multiplying by the sum of the frequencies. So we would expect 13 grids to have 0 trees, 30 grids to have 1 trees, 33 grids to have 2 trees, and so forth. we can look at the observed versus the expected and kind of compare them, and you can see that we are pretty much a match. So it looks like our data follow Poisson distribution. We can check the coefficient of dispersion to confirm, and while it's not equal to 1, it's pretty close. This is a situation and why we need to run a goodness of fit test first. We need to see statistically, is there a difference between our observed and expected, and if there is, then we can look at the coefficient of dispersion to decide if we're clumped or uniform. In this case, coefficient of dispersion suggests that we are uniform because we're less than 1. However, observed and expected are not different. So this is just, we get this value just through random chance. One other thing I want to point out, it's with the Poisson, we don't have any out of numbers. And while our data table went up to 8 trees per grid, where we had zero of those grids, it's possible that we can have 9, 10, or 11. So if these are our frequencies, or our probabilities, if I were to take the sum of all of those frequencies, the sum should add to 1, right? Because we have the sum of all of our outcomes should equal 1. But when you do this, you'll see that we're not. It's not equal to 1. And the reason it's not equal to 1 is because we still have a probability of getting 9 trees in a grid, and 10 trees in a grid, and 11 trees in a grid. For this example, it's not as severe, but if you go back to previous examples, for example, the chickens that were infected with the high-path viruses, and you added up all those probabilities, we would get a total sum of like 0.98, which means there's 2% that's unaccounted for. That's all of the 5 or more days. Do we have to worry about it now? No, we don't. But when we do the goodness of fit test, we will. And we will account for that extra probability in that final category. So here, instead of 8 trees per grid, it would be 8 or more trees per grid, which would increase our probability by like 0.001. All right, so what about the last two columns? Last two columns, we're going to use lambda equals 3. Same thing. Instead of using the mean of the dat, I'm using lambda equals 3 as the mean. We get our probabilities. We get our expected values for all of our Poisson. So that's how we calculate our probabilities. It's definitely easier to do it in R, especially when filling out one of these tables. But it's something that you do need to know because you may need to use the probability equations to generate these expected values in the future. One thing that I will ask you to do is to identify which distribution to use. This would be a separate section on the exam, so a series of questions where I give you the situation, like I do here, and then ask you, should we use a binomial distribution or a Poisson distribution? By doing it this way, we avoid that issue of double jeopardy. So if I asked you to calculate the probability of getting a specific number of bad brake pads in a day, if you use the wrong equation, well, you don't get the right answer, so you'd lose all points. On the test, I'll actually tell you what distribution to use because I'm going to assess, can you use it or not? I'll also assess which distribution is the appropriate one. So here are some examples, different situations, and my question is, should we use binomial distribution or the Poisson distribution? And as you come up with these answers, have an explanation as to why you made that choice. So pause the video, jot down some answers for each of these situations, and with an explanation of why you came up with that determination, and then we'll check our answers. All right, let's go through these. The number of bad brake pads in a day. This is a Poisson distribution. There's no out of number. There's no mention of how many brake pads get produced in a day. We could have 100 brake pads that are made in a day. You can have 10,000 brake pads that are produced in a day. We have no idea what that out of number is. So this is a Poisson. Number of bad brake pads in a batch of 100. This is binomial. We just gave the out of number, so you can have any number from 0 bad break pads up to 100. That's a binomial. Seconds between lightning strikes. This is a Poisson. This is a time 2 event. You could have seconds from, like just after 0 seconds all the way up to infinite, where there isn't another lightning strike. So this is a Poisson. Number of home runs in 15 at bats. Binomial. We have out of. We can have 0. We can have 15. We can't have more than that because it's the out of 15 at bats. Age of first infection. Again, this is a Poisson. This is a time 2 event. You might never get the infection, so it's infinite age, or you can get it very early in life. Time to death, just like infection. This is a time 2 event. This is Poisson. There's no out of number, and time to death could be infinite. Now, you could say, well, everyone dies. Yeah, that's true, but in theory, it's kind of infinite. We don't really have a set time of death. Next one, number of offspring that survive to maturity. Again, we don't know how many offspring were born. You can have 3 offspring. You can have 10,000 offspring, depending on the organism. All right, so the number that survive is, we don't have any out of number. This is a Poisson. Number of offspring out of 1,000 that survive to maturity. Now this is different. Note that we have an out of number of 1,000. So we can have 0 surviving. We can have 1,000 surviving. So hopefully you can see that it's not too difficult. You look at really the out of. Do we have an out of number or not? And if we do, it's likely binomial. If we don't, then it's a Poisson. So on the exam, expect to have a couple of these types of questions where you determine binomial Poisson. And then also expect some probabilities where I will tell you what distribution to use. So next up will be the normal distribution. Normal distribution is a continuous type of distribution, and calculating probabilities are a bit different.